Video course on statistics. From basics to advanced subjects. Dr. Yahya El-Maghazi. Professor Emeritus at Auburn University, Alabama, USA. Former Dean of Science, Technology, Math, Engineering at Ocean County College, New Jersey. A visiting professor at a number of universities including Rowan University, Keene University, and Montclair University, New Jersey, USA.
Dr. Yahya El-Maghazi is the founder and the president of L-Learning LLC, a consulting education organization. You can order a complete set of the course with all video sessions, slideshows, PDF file of the course, test bank, and data bank by visiting Amazon.com.
Probability analysis. Part 1 continued. Probability rules using joint probabilities.
Let's take an example to illustrate what a contingency table means. In a qualifying test for college mathematics courses conducted by one college, 1,000 students took the test. So the total number of students that took the test is 1,000. Out of the 1,000 students, 400 students were male, 350 students were under 22 years of age, and 180 students were male under 22 years of age. If a student is selected at random, what's the chance that the student is male? What's the chance that the student is female? What's the chance that the student is either male or under 22? What is the chance that the student is either female or over 22? As you can see here, we have two types of categories of the data we have. We have the gender, male and female, and we have the age, which is under 22 or over 22. So once we know the categories, and these are two categories, then we can develop the so-called contingency table, where the one category will be in a column, the other category will be in the rows. So the male and female in the column, the age will be in the row, and we can add a column here called total, and we add another column here to a row called total. So you can see here that this is the initiation of a contingency table, which is an effort that we have to make in order to be able to handle this type of problems. Now, we were told that the total is 1,000. So that 1,000 would be the overall total will have to come in this square here. So we have a total of 1,000. We were also told that we have 400 female. So at, 400 male. So at the male total, we have 400. So the overall total is 1,000, and we have 400 male. So you can see here we're filling in the gaps or the cells in the table. We were also told that we have 350 students that were under 22. So this is the total for under 22. We have 350. We were also told that we have 180 students that were female under 22. That is female under 22. So that 180 will have female under, it was male under 22. So it will have to come in this cell, which represents male under 22. So from the givens of this problem, we were able to insert the number in their appropriate cells. The total was 1,000, the total male was 400, the total under 22 was 350, and the male and under 22 total was 180. Now once we do that, we can then complete the table in many different ways. Since we know the table, the totals, then we can always find the missing number. For example, we have 1,000 here, so if this is 350, then this will have to be 650, meaning the 350 plus 650 will give us the 1,000. Similarly, since we have 400 here, and this is 1,000, and that's the total, then this number will have to be 600. And we can move on. 350 will give us a sum of 180 plus 170. So where do we get this 170? It's the 350 minus the 180. Now, since the total here is 600 and this is 170, then this should be 430. Finally, since the total here is 400 and this is 180, then the number here should be 220. So we use the given numbers, and then by subtraction or addition, we can find the rest of the numbers in the contingency table. And once we have this table filled with the numbers, then we can move on to answering the questions. And the way we do that is to convert this table here into a probability table. So here is how we do it. Here is the original table, and here is the table that we are trying to reach. And notice something here. The total here is 1,000. That is because it's a total of observations or total of outcomes. But if it is a total of probability, then that 1,000 will have to be converted into a sum of probability, which is, as you can see here, 1. So notice how we start. The first number we put in the probability table is 1, which corresponds to the sum of 1,000. Now, if I want to develop a probability table, it will be useful to develop a table describing the different events. So here is U representing under 22. Here is O representing over. Here is M representing female. Here, male. Here is F representing female. Here is the probability of male and under. This is the probability of male and over. This is the probability of female and under. This is the probability of female and over. This is the probability of male. This is the total male, as you can see. This is the probability of female. This is the probability of under total. This is the probability of over total. So you can see here that we are about to calculate probabilities that are corresponding to these numbers, and these are what we call marginal probabilities. For example, the probability of male. Well, if I look at this table, I find that the total number of males are 400. And the overall total is 1,000. So it's obviously 400 divided by 1,000, which will give us the probability of male. That 0.4 number here will have to be put in correspondence to this number. So if this is the male, instead of the total of male, we're going to put the probability of male, which is the 0.4. Similarly, if we go to the probability of female, we see here that the total number of female is 600 divided by the total of 1,000. That's 0.6, and that will be put here. If we go to probability of over, all over are 650 divided by the total of 1,000. That's 0.65, and this will have to come right here. Probability of under, all under are 350 divided by the total of 1,000. That's 0.35, and this will have to come here. And exactly as we did before, by adding and subtracting values in the contingency table, we can do the same thing with the probability table. If this is 1, as you can see here, this is we have an 0.4 plus 0.6. Again, 0.35 plus 0.65. So you take it this way or this way, that will give us a sum of 1. Now, suppose I'm talking about the probability of male and under. Now, male is here, under is here, so male and under will be the 180. This is the number of people that are male and under 22. If I divide this by the total 1,000, that will give us the probability of male and under. That's a coexistence events. So that will have to be the 0.18 has to be put where? In this cell here, the male and the under. Similarly, the female and over. If we look at the female and over, we have 430 divided by the total of 1,000. This will give us 0.43, which will have to come right here. Female and over. And as you can see, we now can complete the table. Given that these are the totals again, and these are the individuals, we can complete the table, and that complete the contingency table probability. So here is where we are now, and if we are here, we can add more questions, such as what is the chance that the student is either male or under 22? Okay? We told you before in the previous session that either male or under, if these are mutually exclusive, meaning that students can be male and under, then we use the law of PA plus PB minus PA and B. And that's what we did here. P male or under is equal to the P male plus the P under minus the intersection or the coexistence part, which is P, M, and U. Well, P male, we know male is 0.4. B female, here it is at 0.4. B under, that's it. This one here, 0.35. How about the B male and under? Well, male and the under would be this portion here, the 0.18. And again, from the table, we were able to immediately calculate the probability of male or under. Similarly, if we are trying to do the female or over, it's the probability of female plus the probability of over minus the probability of female and over. So once again, the 0.6 is the probability of female, the 0.65 is the probability of over, and the probability of female and over is the 0.43. And as you can see, these are all derived directly from the table. That is how easy it is if we use a contingency table to calculate the different probabilities. Here is another example. We'll go over it real quickly. In a public school, the issue of dress code was brought up as a result of some apparent violations. 300 students categorized by gender were asked about their opinion. We have again male and female in this column. That's one category. And the other category is whether the students agree, disagree, or there is no opinion. You can see here we have more divisions of the category here, not 2 and 2 like the previous example. And once again, here is the contingency table. We have 300 students entirely surveyed. We have 120 male and we have 180 female. We had 104 students that agreed to the dress code. We have 135 that disagreed, and we have 25 that had no opinion. So you can see that the contingency table has given us a cross frequency so that we can know the number of students that belong to any one of these categories: male and agree, female and no opinion, male and disagree, and so on. And by having that, we can answer any question. What's the probability that a randomly selected student from these 300 students will agree with the dress code or has no opinion? That's either or. And so on, as you can see on the screen. Let's take some of these probabilities. First, we convert the table into probability table. And here is the definition of the different probability as we did before. And very similar to what we did before, we can convert the contingency frequency table into a relative frequency or probability table, just the same way as we did before. And by doing that, we can start with the marginal probability. Probability of A, or agree, will be the 140 divided by the total, which is the 0.467. Probability of disagree will be the 135 divided by the total. Probability of N, probability of M, probability of M. You can see here that we are following the same example that we covered before. So it's very important that we convert the contingency table into a probability table. Here we can go to union probability, the rule of addition, such as the probability of agree or no opinion. Now notice that these are mutually exclusive events. If a students agree, that means they will have to agree. They cannot agree and have no opinion at the same time. That's what we mean by mutually exclusive event. And the rule of addition in this case is PA plus BN, where PA is here, you can see from the table, and BN is here. So just by adding these two, it will give us the PA or N. If we say P female or agree, now we have an overlap here. You could be a female and agree, but you could also be a female and disagree. So what we have here is PF for A is PF plus BA minus the overlap of F and A. Now PF is the female, which is the 180 divided by 300, which is this value here, 0.6. P agree, which is, look at the total of agree, 140 divided by 300, which is the 0.467 here, minus female and agree, that is female and agree, that's 60 divided by the 300, which will be the 0.2 value, which is female and agree, and you can get it here from the table directly, and that gives us the probability of F or A, and so on. Now that takes us to another important subject, which is conditional probability. That's the probability of A given that B has occurred. The best way to get a conditional probability is via the contingency table that we just discussed. It is the probability that an event will occur given that another event has already occurred. If A and B are two events, then the conditional probability of A given B or BA given B will be given as follows. BA and B will be equal BA times B, B given A. What we are interested in is B given A. And what you see here, B given A is equal P, A and B divided by P, A. And this makes sense because the probability of B given that A occurred, okay, will have to be this portion here, the B, A and B, the coexistence portion, divided by the probability of A, since it is given A that has occurred. Let's go back to the contingency table and see how we calculate the conditional probability from a contingency table. In this case, the question is, what's the probability that the person being surveyed agreed given that the person is a male? So that is agreed given that it's a male. That's PA given M. Following the rule of conditional probability, it is PA and M divided by PM. Well, PA and M is a coexistence of agree and the male. So that is the 80, okay, divided by the 300. While given the M, or the probability of M, that's the male, that's 120 divided by 300. So we have this value and we have this value from the contingency table. The 80 over 300 will give us the probability of A and M, and the 120 divided by 300 will give us the PM. However, if we look at the contingency table carefully, we can get A given M directly without having to use the ratio here. If you look at here, this value here is 80, which is the male given that they agreed. Now, divided by the total male, which is the 120, that should give us the answer directly. So there are two ways to solve this problem. Either by looking at PA and M, okay, which is the 80 divided by 300, and divided by PM, which is the 120 divided by 300, and as you can see, 300 will cancel out in that ratio, and that will give us 80 over 20, or directly from the contingency table, we have here PA given M, we have 80 divided by 120 will give us the PA given M directly. We can also illustrate the conditional probability using a tree diagram. Let's look at this case here. We have male and female. Now, the probability of male is 120, that's the male, divided by the total, which is 300. That's obvious. The probability of male is 180, which is the total female, divided by 300. Now, as we move on into male that agree, male that disagree, male with no opinion, now we have conditional probability. That is agree given the fact that it's male, or disagree given the fact that it's male. So agree given that it is male, here is the agree given that it is male. So the top number will be the 80, which is the coexistence of agree and male, and the bottom number will be the total corresponding to the male. Same thing, disagree and male. This is disagree and male. We have 30, okay, divided by 120 since it is given male. And so on. You can develop a tree diagram straight from the table, and that gives us the conditional or the different conditional probability by the tree diagram. We move now into the so-called independent versus dependent events. Two events are said to be independent if the occurrence of one does not affect the occurrence of the other. If you toss in a coin twice, then the occurrence of head in the first toss will not affect the occurrence of another head or tail in the second toss. So that will constitute two independent events. The general rule for independent events is as follows. If the PA given B is equal to PA, then the two events A and B are independent. Meaning if P, the probability of A, conditional by B is PA, then the two events A and B are independent. Similarly, if PB given A is equal to PB, that means that A and B are independent. Let's take an example. In the example of students' opinion on dress code, we have events male and disagree. Let us examine these. The events of male and disagree. Are these independent or dependent? Meaning is whether disagreeing with the dress code has anything to do with the fact that the student is a male. Or are they dependent or independent? So events M and D are independent events if PM given D equal PM. So let us see what's PM given D. Well, PM given D is 30 divided by 135. As you can see here, PM given D is 30 divided by 135, which is the total disagree. PM, on the other hand, is 120, the total male, divided by the total 300, that's 0.4. Now, as you can see here, the two probabilities are not the same. And if the two probabilities are the same, then the M and D events are indeed dependent. And that's very important to know, that the fact that some students disagreed will depend on their gender being male. Similarly, if we're talking about female and disagree, in order for female and disagree to be independent, PF given D will have to be equal PF. And if we calculate each independently, we see that the two probabilities are not the same. And what does that mean? It means the two events are dependent, meaning to disagree with the dress code had something to do with the fact that the student is a female. That is dependent events. Finally, the multiplication tables. We multiply the probability of A and B, which is the coexistent probability that we mentioned many times, can be for dependent events. If the two events A and B are dependent, can be determined from PA times PB given A. That is the multiplication rule. Here is an example in a survey by a company regarding an optional retirement package. Employees were divided into junior 5 to 10 working years and senior above 10 working years. If one of these employees is selected at random for membership on a retirement committee, what is the probability that this employee is a junior and approves the retirement package? Now here is our table again, and the question is, what's the probability that this employee is a junior? Okay, here is the junior and approves the retirement package. That's the 22, as you can see, the coexistence. Now, the probability of junior and approve by the multiplication table of dependent variables is Pj times Pa given j. And as you can see here, Pj is 44 divided by 100. Where we come up with this from, here is the total junior of 44 divided by the total number, which is 100. That's 44 divided by 100. The probability of A given j, this is the 22, but given j, meaning the total of j, which is the 44, so that's 0.5. So by the rule of multiplication of dependent variables, Pj and A is equal Pj times Pa given j. 0.44 times 0.5 gives us 0.22. Or we can go straight forward to the contingency table and get Pj and A being 22 divided by the total, and that will give us the probability of J and A for dependent events. Here is another example. In a box of 30 DVDs, 3 DVDs are typically defective. If 2 DVDs are selected randomly, one after the other from a box of DVDs, what's the probability of selecting a defective DVD followed by another DVD? That's straightforward. We have 3 DVD altogether, 30 DVD altogether. We take 3 divided by 30. That will be the probability of first DVD is defective. And if we are trying to calculate the probability of the second DVD to be defective, given that the first one was, now we are taking 1 already, so we have 29, and what's left for us, since the first one was taken, is 2 defective DVDs, so that's 2 divided by 29, and of course the probability of selecting a defective DVD followed by another will have to be the multiplication of these two values of probability. So what we covered so far is continuing with the rules of probability, but this time we try to implement or use the different rules of probability, starting with the marginal probability. These are the straightforward probability, going into the addition rules of probability, then moving into the conditional, and then moving to the multiplication rules. And we were able to do all of these rules using the cross-frequency table or the contingency table. I believe that the use of the contingency table is very useful to describe many applications, but if one wants to understand all the rules of probability in one example, then an example of contingency table can cover all of this, and that close the session of classic and empirical probability. The next session will be dealing with probability distributions.
Video course on statistics. From basics to advanced subjects. Dr. Yahya El-Maghazi, Professor Emeritus at Auburn University, Alabama, USA. Former Dean of Science, Technology, Math, Engineering at Ocean County College, New Jersey. A visiting professor at a number of universities including Rowan University, Keene University, and Montclair University, New Jersey, USA.
Dr. Yahya El-Maghazi is the founder and the president of L Learning LLC, a consulting education organization.